Good afternoon, everyone. Let's start our class, okay? I need to record first. Okay. Tuesday afternoon, we have talked about what's hydronics. First, we introduce the definition of fluids. What's a fluid, right? We first introduced the difference between fluids and solid in molecular levels. Okay, for solids, their molecules are just close. They stick to each other. But for fluids, the position relative for gas actually they just move freely, right? And so as a result, solid has a fixed shape and fixed volume. For the fluid, always remind yourself fluids include gas and liquid. For us, civil engineers, for this course, hydraulics, we just focus on liquids. That means hydraulics only study the phenomenon of liquids, okay? And also, which introduced a very important boundary condition for fluid. When fluid moves, when fluid contact with a solid boundary and when it's moving past the solid boundary, there is a very important boundary condition we call the no slip boundary condition. That means the fluid will have the same velocity with the solid boundary, or the relative velocity to the solid will be equal to zero. So that's why when there is two plates, one is fixed, the upper is moving with a uniform velocity u, the fluid contact with the lower plate, the velocity is also equal to zero, while the velocity of the fluid contact with the upper plate will be equal to the velocity of the moving plate, u, okay? And we can say this movie to be more clear about no slip boundary condition. Near the bottom, and then you see here, we have this dye injection at the bottom because the no slip boundary condition, because the bottom is fixed. So the water will be stagnant and the flowing water will form a stagnant layer. That means their velocity will equal to zero. Okay. And however, if we move away the filament and we will see the motion of the water. Okay, we can watch it again. This is the no slip boundary condition. You should always keep in mind that for fluid, for real fluid, they will have the same velocity with the solid boundary they contact with. Okay, this is a dye experiment, okay. Okay, and then we introduce the definition of the fluid in technical point. And before that, we need to know that for the force, internal force, we have the tensile force, compressive force, shear force, right? We know that in material mechanics, the material mechanics, if there is a sling cylinder, we pull it, there will be tensile force, right? There will be tensile force, and also in charge with it also can we have the compressive force, and but also there will be shear force. Shear force means the force will within the plane, right? Is inside the plane, just like this is the pull force, the tensile force, but the shear force also is in the plane. That's shear force. And also corresponding to tensile force, compressive force, shear force, we have the deformation. For tensile force, it will be just means like the cylinder, slim cylinder is stretched, right? And so we got the string, the string, and or the linear deformation, right? Just like for this cylinder, uh, sorry, cylinder, this is elation length, and we just apply a tensile force and it will get stretched. We have this linear deformation, right? And for compressive force also, it will have the linear deformation. But for the shear force, we have we corresponding to the shear strain. What's the shear strain? Just like with this is an element for the fluid element, for the solid element, and it can change its shape. We just take an example. This is a rectangular fluid element or solid element. If we apply shear force, and then the rectangle will deform, it will deform like this. Okay, this angle is not rectangular anymore. So we call this a shear strain, and a shear strain will have the shear stress, and shear stress is actually the shear force per unit area. So this one is due to the shear force. Okay, so before we talk about the shear stress, we need to understand what is shear stress. So we just call back what we have learned in material mechanics. Okay, so we need to know what's tensile force, compressive force, shear force, right? Or maybe for you, again, I will like this way. Maybe this is element. Okay, so we take cubic. Sorry, for my drawing. Okay, so we have the. Sorry, can't find it. Okay. So we have this force, right? And then we have its normal component and its tangential component, and tangential component is on the plane, and so this one is called shear force. Okay, this one is called tensile force, is pulling out, or it's a compressive force if it's compress the cubic element. Okay, so for fluid, they can't resist, tensile force. So they can't they have no ability to resist uh, uh, linear deformation. But for the fluid, we know that it can resist compressive force. For example, the gas can be compressed, right? So it's obviously fluid can resist the compressive force. About the shear force, whether the fluid can resist the shear force, actually, Tuesday afternoon, we already talked about this. Okay, we know that for a solid block, it can resist the shear force with a fixed shear deformation. Okay, so this is what we have learned before, right? For solids, they can resist shear by static deformation. Okay, so this you see here, this is the original solid, and then the solid under the action of the please mute. Okay, after if we apply a shear force on the solid, it will have a static formation, and that means the solid, just like this angle, right? It's called shear deformation. Okay, and we have this hook relationship, hook equation, hook formula. The shear stress is the shear stress is linear to the shear strain, where G is the shear modulus. This is what we have learned in material mechanics, right? But however, for fluid, if there is also the pulling force, and then there will have the shear force applied to on the solid surface. So not like the solid, it can resist this shear force with a fixed or a static deformation. The fluid will keep deforming. Okay, under the action of the shear force, the fluid will keep deforming no matter how small the shear stress or shear force it is. Okay, so just like from this movie, we can see it. The inner cylinder fixed, the outer is rotating. You will say when the outer cylinder is rotating. Okay, we use dye filament to show there is a small rectangular fluid element, and this one is located in the space between these concentric cylinders. For this concentric cylinder, the inner wall is fixed. So, according to the no-slip boundary condition, the fluid contact with the inner wall also have the zero velocity, right? And the outer wall is moving with angular speed equal to omega. So the velocity will be equal to omega times the radius, right? Again, according to the no-slip boundary condition, the fluid contact with the outer wall also have the velocity with the outer wall, right? And if the outer wall keep moving and the fluid element is also moving, and actually the fluid element undergoes angular deformation, and it will not stop. It will not stop. Okay, again, you can say this. That means the fluid element will continuously deform under the action of the shear stress. Okay, the shear stress is actually, we know shear stress is the shear force per unit area. Okay, shear stress is the shear force per unit area. It will have the same unit with pressure, because pressure is the pressure force per unit area, right? So shear stress is also the shear force per unit area. So shear force actually behave like the friction force, right? Just like you say this, we can regard the fluid as layers, okay? As layers, we have just the layer contact with the outer wall, and then just like the fluid the fluid, the fluid layer, fluid layer, fluid layer. So this outer one is moving, and definitely if this one at the beginning it's static, and according to what we have learned before, and this null layer will drag out this outer layer, right? They will have the internal friction force. Okay, so for the shear force, actually, we can also regard it as internal friction force between fluids. Okay, so accordingly, finally, when we say what is a fluid, we say a fluid undergoes continuous deformation under the action of a shear force. Or we can say, no matter how small the shear stress is, the fluid will continuously deform. Okay, so this is a definition of fluid. Or maybe we can say the difference, the really dominant difference between a fluid and solid is the whether it's easy to deform. No, it's not easy to deform. So we mean the continuous deformation. Okay, that's the difference between the fluid and solid. And also we introduced a very, very important assumption, continuum flow. We just know that we assume that the fluid is continuous. The fluids as continuum, what does that mean? It means in the fluid mechanics course or in this hydraulics course, we don't study a molecule. We study a collection of molecules, or we study fluid element, or maybe we call fluid particle. If we ignore the mass, we call it fluid element. We call it, oh, sorry. If we just ignore its size, we call it a fluid particle. Okay. So instead study fluid molecule, we study fluid particle or fluid element. So as a result, the properties of the fluid are point functions, or they are single valued at a point. Is very, very important. Okay, we take an example here. Okay, so actually for the point A, we got thousands of molecules, but actually we just can just tell the velocity at point A, the pressure, the density at point A is actually a statistic average values of these molecules. Okay. We also say that we just take example here. We always say we should have enough molecules inside the fluid element. The smallest size we study in fluid is fluid element. Inside the fluid element, we should have thousands of molecules, just like here. Volume fluid to which instrument response, you say if the molecules is not enough, the density will vary with the molecule numbers. But with the increase of the molecule size, the density is almost constant. It will have a average static value. Okay. So this is a very, very important assumption of fluid. We assume fluid is continuum. Okay. This is very important. Or maybe we can say that the fluid essentially is not continuum, but for engineering problems or for the purpose of investigation, we just assume the fluid is continuous. Okay. So we can use what we have learned in calculus, right? It's a continuous function. We can take the first derivative and the second derivative, okay? Density, and today we'll start to continue introduction, some important properties of fluid, okay? Density, we are quite familiar, right? Density is defined as its mass per unit volume, okay? So the density have the unit of kg per meter cubic. So its dimension got mass, got length, right? We know that for any secondary quantities, they are composed of the primary dimensions, that's length, mass, and time. Okay, or length, time, and force. So here you say density is actually a combination of mass and length. Okay. For density, we know that for fluid includes liquid and gas. So when we talk about their properties, sometimes we need to tell it's liquid or gas because they have different performance. For the liquids, their density change with later with temperature and pressure. They are almost fixed values. And for example, for water, you say when it increases from 4 Celsius to 15 Celsius, the density just only have 0.1% variation. Okay. However, for gas, its density changes dramatically with temperature and pressure. So that's very important when you talk about when you talk about gas, you need to be very clear about its temperature and pressure. Okay. And sometimes instead of use density, we use specific volume, especially for thermodynamics. Specific volume is a volume per unit mass and is therefore the reciprocal of the density. Okay, sometimes we will use this. And another variable we often use is the specific weight of a fluid. Specific weight of a fluid, we use gamma. This is gamma, Greek variable gamma to indicate the specific weight. Specific weight gamma is equal to density times gravitation. Okay, G. Okay. Um, so that's density. And sometimes for two fluids, even their density are equal, but they still have quite different performance, different. Just for example, here we have uh, uh, this movie. We can see here we have two fluids. They look like, yeah, they they even have the same density sometimes. But you say when we pour from one glass to another glass, they just behave totally different. One is easy, just maybe you only need to 1 second to with it. That's water. Pour water from this glass to another glass, just 1 second. But for this one is actually silicon. It takes times. So maybe we can say for these two different fluids, one is easy to deform, right? The other is not easy to deform. Okay. For these two fluids, even they look like clear and have the same density, but they behave very differently. Okay. So why? The deformation why is easy, another is difficult. So we introduce a very important fluid property to describe the resistance to deformation. Okay, viscosity. Viscosity is actually introduced to uh, measure the resistance to the shear motion. Okay, so when a fluid is sheared, we say when the fluid is under the action of shear force, it definitely will begins to move, right? Because no matter how small the shear force is, the fluid will keep moving continuously, right? Will keep deforming continuously. A pair of forces appear on the shear surface which resists the shear motion of the fluid. This is called viscosity. The shear motion of fluid is definitely kind of deformation. So viscosity is a measure of fluid's resistance to shear. Obviously, more viscous, more resistance, so more difficult to deform. Viscosity is actually the intrinsic property of a fluid. It varies with temperature And we will see when temperature increase or decrease, what will happen to viscosity. It's because of the viscosity, it causes these fluids to adhere to solid boundaries. Or it's because of viscosity, we have the important no slip boundary condition. It's very important. Viscosity, just like we say, it's just like the friction force, it's internal friction force. The viscosity is just like the friction coefficient. Okay, the larger viscosity, the more difficult to move, right? To have relative motion to deform, right? So it's because the viscosity is because the friction that fluids can adhere to a solid boundary. I think we can understand this, right? If we don't consider the viscosity, whether the fluid can adhere to solid boundary or not, think about it. If we assume the viscous fluid viscosity is equal to zero, we often call the ideal fluid. For ideal fluid, it will adhere to solid boundary or not. For ideal fluid, whether it will have the no slip boundary condition, can you tell me? If there is no viscosity, if there is no friction force, what will happen? There will be no slip boundary condition, right? Just like when you stand on the ice, there is no friction. You will move, right? So for ideal fluid, it's very important here. For ideal fluid, there will be no solid boundary condition anymore. Just like this is solid boundary, it's fixed. However, the fluid, if we regard it as non-viscous, have no viscosity, and so the fluid contact with the fixed solid boundary still have the tangential velocity. Sure, the normal velocity will equal to zero because the fluid can't go into the solid wall, right? It's very important, okay? So for the viscosity, one more thing we need to understand what decide the friction force between the solid and the fluid, because we know for the solid we have the also friction force. Okay. Here we got a very famous example. There are three discs, a regular one, a wax one, a sand one. They were hung by slim metal wires, and except for the disc, except for the surface, a little bit the service are different. Just like for the service is we don't do nothing to the service, but the one we just waxed. Why we waxed the service? To decrease the friction coefficient, right? To make it smooth. And the sand one, why we sand it? The friction coefficient of the surface will increase, right? So for the three discs, the friction coefficient, this last one is the smallest, right? This one regular is larger, and the sand one is the highest, okay? And everything will be the same except the friction coefficient of the disk, okay? If we move the disk away from its balance location and then we leave, what will happen? It will behave like a pendulum, right? It will swing back and forth. But because of the drag force by the water, right? Because of drag force by the water, it will finally stop. How do you think the duration of an oscillation for three disks? How do you think the duration of oscillation for three disks? Can you tell me? Can you try your answer? Which one equal for all? You know the answer already because you have seen the PPT, so it's not a surprise, right? Yeah, Yeah, thank you very much. But why they are equal? The duration time will be equal for three disks. Do you know why? Why don't you think? Because the third one will just stop 1 second, and the last one will just stay longer. Why? Because it's very important. Yeah, you're right. That the uh, they have the equal duration of oscillations. Why? Because yeah, it's you are right that because of the drag force by the water, because of the friction force between the water and the disc stop to swing back and forth. And this friction force is decided by the fluid, is decided by the fluid viscosity, not by the solid boundary. Okay, it's very important. The friction force between the solid and liquid is decided by the fluid viscosity. The larger the fluid viscosity, the larger the friction force between the solid and the fluid. Okay, so all here, this one is a little bit say one. Just we say the friction force, okay, is because of the fluid viscosity. Or you can say this one. If this is water, right? We just the this can swing back and forth for just 10 seconds or 20 seconds, we don't know. It's up to you, right? Because of the so, but if we replace the water with the silicon, what will happen? The disk will stop 1 second, right? Right away. So that's also can tell you that also can tell you the the friction is due to the fluid viscosity. Okay. So just now we said the friction force uh, is actually is decided by the fluid viscosity. So this one we have the formula by Newton. Again, Newton second law, the same person. Okay, really, really great one. Okay. Again, we consider flow between fixed and moving parallel plates. Again, it's Coulomb flow. We also, this is the experiment by Newton, okay? Again, because of the no slip bond condition for viscous fluid, okay? So the fluid contact with the lower plate will have the zero velocity, and the fluid contact with the upper plate will have the velocity equal to u, and the velocity profile is linear and is a function of y only. That means velocity the velocity not change with x. Okay, so this is a very famous law, and from Newton, he found that we just give this directly. Okay, later on we'll introduce again the shear stress. Again, here tau is we know it's shear stress. Okay, so just like this one and that upper one want to move, want to go forward. So the lower one will drag it behind, right? So we'll have the internal friction force. This is also called the shear force, and the shear force per unit area is called the shear stress. Okay, for this shear stress, Newton found out that it will equal to the fluid viscosity. This is fluid viscosity times the spatial derivative of the velocity. Okay, so this is the velocity. This is the coordinate y, and Newton found this function. Okay, here it's very clear that tau, the shear stress, is linear proportional to the viscosity, and also it's proportional to the velocity gradient. Okay, it's not proportional to the velocity magnitude, but the gradient. Okay, and if here because here the velocity is given is linear proportional to y, and this one is constant. So we can find out that the shear stress is a constant. Okay, this is derived by Newton, and from this formula, we know the shear stress is decided by the velocity gradient, not by the velocity magnitude. Also, you say because fluid can stand any shear stress, so the fluid viscosity will only affect its flow speed, but can't stop the flowing. Okay, no matter just how hard it to change, but it still keep deforming. Okay, just like you pour the silicon. Okay, now fluid viscosity, we use this Greek variable mu to indicate the fluid viscosity. This one is called absolute or dynamic viscosity. Its dimensions, again, is a combination of mass, length, and time. Okay, mass, length, and time. And also we can use the unit per second to indicate. You can derive this. You can use this formula to find out. You can use the formula. Oh, viscosity coefficient is constant or not? We will see that later. Okay, so it's a very good question. Okay, the fluid viscosity, here we use mu Greek to indicate the fluid viscosity. Is called absolute dynamic viscosity. Okay, this fluid viscosity we know is actually the internal or in the friction force. This friction force is actually decided by two factors. We know one is the attractive forces between molecules, right? You see, you hear this is the upper layer, this is lower layer, and so when upper layer move forward, the lower layer will apply the friction force or the shear stress, right? You see, this one, you can see the green one, arrows, right? This is the force because the attractive force between molecules, you go forward, I don't want you to go away from me, so I just drag you behind. Okay, so attractive forces between molecules actually is one important reason for the friction force. And another thing is the molecules, they are moving here and there, so they bump into each other. They will have the moment transfer, right? We know that if two cars bump into each other, if they collide with each other, there will be moment transfer, there will be forces, right? So another important factor for friction, for this internal friction force, is because of the thermal movement of the molecules. Okay, so you say two factors influence, have effect on the viscosity, or we can say they are dominant factors to decide whether it's easy to deform or not easy to deform, or to decide its resistance to shear stress. Okay, so for fluid, we know fluid include liquid and gas. For liquid, the most important thing for liquid is the molecules, they still, the molecular forces are medium, okay? They have relative motion, the motion is not strong enough. So for liquids, the attractive forces between molecules is a dominant factor for the viscosity. However, for gas, we know that for gas because the gas molecules, they just the molecular attractive forces is almost equal to zero. So for gas, the dominant factor to decide its viscosity or decide its resistance to deformation is the moment transfer due to the thermal movement of molecules. So I would like to ask you, when the temperature increase, the viscosity for liquid will increase or decrease. When the temperature increase, what will happen to the viscosity for gas? Oh, that's the same. Yeah, you have preview. So can you tell me when the temperature increase, what will happen to the fluid viscosity? Whether it will increase or decrease? You can tell me. Or both? Or it depends. It depends it's liquid or gas, or depends it's water or gas. You see, for the water, for the liquid, the main factor for the viscosity is the molecular forces. Okay. When the temperature increase, their distance will be further away, right? That's what I always say. It's too hot. Don't be too close to me. Okay. Move away, stand away. So the distance between the molecules increase. And so attractive forces between molecules decrease, right? Closer, larger the molecule forces. The temperature increase, so the molecules will be further away. The molecular force decrease, so the viscosity decrease. For water, this is for water, right? However, for gas, when the temperature increases will become hot, the movement of the molecules will be more frequent, right? In the winter, nobody want to move, but when it starts to be hot, people like to go out, right? So when the temperature increase, the molecular of the gas molecules will have frequent motion, will have frequent movement. So the viscosity will increase because they will have more moment transfer. So it's very important. When we talk about the viscosity change with the temperature, you need to know is for liquid or it's gas. Gamma uh, we found tau is the shear stress equal to gamma g gamma. Oh, that's one. Yeah, you asked a very good question. I know.
Fast
Yeah,
flight.
yeah, I know what you're talking about. It's very good question. I'm just really appreciate this. That means you are really listening. That's very good. Okay. So I forgot to talk about this. When we talk about the difference between solid and liquid, right? Just like here, what? Oh, yes, you just asked a very good question. It's a very important difference between solid and liquid. Definitely, tau is shear stress for solid also. Gamma here is shear strain. It's shear strain. Okay, it's shear strain. It's just have the
next slide we find that its specific weight of fluid gamma is equal to.
Yes, this is, I mean, just let me finish this. This is for solid. The shear stress here, gamma is shear strain. But however, for flute, now let me write down here. Okay, I think I know what I should do later on. For this one, mu du dy, and later on we can see still use gamma. But this gamma is not shear strain, it's shear strain weight. Oh, it's very important. Means this is shear strain per second. Okay, again, yes.
Lakshya, here G is constant, right?
Yeah, G is constant. The shear
And
modulus
Lakshya,
is
then
constant.
what's the value of the G?
What is what?
Actually, Lakshya, I'm asking what's the value of G?
Oh,
Shear
value
modulus.
of G. Oh, this
Yeah.
value of G, you need to refer to your material mechanics textbook. You can find out the shear modulus for most materials. This shear modulus is given directly just for steel, for copper. We can just use the value just directly. You can refer to any textbook. You know this, okay? Shear modulus. This is what you have learned for material mechanics. Okay.
Okay, Lakshya.
Okay. Here, gamma is shear strain, but for us fluid, gamma is shear strain weight. Is shear strain per unit second. It's very different. Just like du dy, do you know du dy? Can you find out the dimension of du dy or the unit? U is the velocity, right? And here U is velocity. And y, this one is velocity. This one is the distance. And again, for you, your material mechanics, here U is displacement. You say for solid, U is displacement. Do you know the difference? So we have du dy, but here U is a velocity. For solid, U is displacement. So velocity is displacement per second, right?
Yes, Lakshya.
Yeah, it's very important. So that's why fluid mechanics or hydraulics is more difficult, because here we will see the function and the equation we deal with will be nonlinear equations. That's why, because we got the velocity involved. Okay, so yeah, you can see they look not same. Yeah, we still use gamma, but they are totally different. Okay.
Okay, Lakshya. I got it.
Thank you. Thank you for your question. I'm sorry. Sorry. Maybe we take a 10 minutes break. Okay, sorry.